In this activity, we shall be learning how to verify the ratio of areas theorem of class 10th. The objective of this activity is to verify the statement or the property of a triangle that the ratio of areas of two similar triangles is equal to the ratio of squares of their corresponding sides. We'll be performing an activity to verify this statement. Let's see the concept in hand. When you have two similar triangles, suppose this is triangle ABC and it is similar to another given triangle, suppose the other triangle is named as PQR. If these two triangles, that is triangle ABC and the other triangle, triangle PQR, are similar, then the property of ratio of areas states that if you take the area of the first triangle and take its ratio with the other triangle, the area of the other triangle, then these two areas will be in a ratio which will be equal to the square. Let's take AB in this case, then you'll have to take PQ in this case because they are corresponding sides. So if you square AB and you square PQ, if you take that ratio, the squares, then this ratio will always be equal to the ratio of areas of the two similar triangles. Likewise, if you take BC in the first triangle, so you take BC square as the numerator, you will have to take QR square, that is the corresponding side in triangle PQR, as the other side. And the third one, if you take AC square, then you will have to take PR square. So the ratio of areas of two similar triangles is equal to ratio of squares of their corresponding sides. This can be verified experimentally using the following material. We need a chart paper, a construction box, a pair of scissors, and glue stick or Fevicol. Using all these materials, let's see how we can perform this activity.
For verifying the ratio of areas theorem, we need to take cutouts of fluorescent sheet of paper. You can see I have taken an equilateral triangle, and this equilateral triangle is of side 5 units. So the unit can be anything depending on the size of the paper. It can be centimeters or inches. Likewise, you have to take a cutout of 3 units. That means this equilateral triangle has a side 3 units. So 5 units and 3 units. After cutting out these two triangles, we have to name the triangles. Let's name this triangle as ABC and this as DEF. The points here are labeled as P1, P2, P3, P4, and the points here are labeled as Q1, Q2, Q3, Q4. So these points divide the side AB into 5 equal parts, and these 4 points divide the side AC into 5 equal parts. Likewise, the other triangle is named as DEF, and we mark points R1 and R2 on this, which divide the side DE into 3 equal parts, and mark points S1 and S2 on DF, which divides it into 3 equal parts. So after having named all these points, we will be drawing some lines, and those lines will look like this. You can see here all the namings have been done now. The lines which we have to draw are shown here. So we join P1 Q1, P2 Q2, P3 Q3, P4 Q4. Likewise in this one, R1 S1, R2 S2. And then parallel to AC, we draw line from P1, this line from P2, this line from P3, and line from P4. So all these lines are parallel to AC. And similarly, parallel to AB, we draw lines from Q1, Q2, Q3 and Q4. So you will obtain a figure like this, in which the big figure is divided into 25 similar triangles. Likewise, the same thing is to be repeated for the smaller triangle. In this triangle, we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 similar triangles. And after dividing these two, we can derive the result directly, because the area of this smaller triangle DEF, if you call area of one of these triangles as 1 unit, then this is actually 9 units. And if you take the ratio of this with area of the big triangle ABC, what is the area of this triangle? If you call this as 1 unit, then there are 25 small triangles, and therefore it is 25. But this 9 upon 25 is actually 3 upon 5 whole square, because 3 square is 9 and 5 square is 25. And what is 3? 3 is the side of the smaller triangle, that is DE. So we can write it as DE, and 5 is the side of the larger triangle, that is AB. So if you separate out the square, you will get DE square upon AB square. And that's what was required to be proven, because area of two similar triangles, the ratio, will always be equal to ratio of squares of their corresponding sides. So I have taken DE here as 3. You can take EF, but if you take EF as 3, then you will have to take BC as 5. Hence, this activity is completed.